Chapter 2. Simple Sorting and Searching Algorithms. Searching and sorting topics. Searching linear/sequential search. Binary search. Sorting bubble sort. Insertion sort. Selection sort. Common problems. There are some very common problems that we use computers to solve. Searching, looking for specific data item/record from list of data items or set of records. Sorting, placing records/items in order. There are numerous algorithms to perform searches and sorts. We will briefly explore a few common ones in this lecture. Searching. A question you should always ask when selecting a search algorithm is, how fast does the search have to be? Facts. In general, the faster the algorithm is, the more complex it is. You don't always need to use or should use the fastest algorithm. The list to be searched can either be ordered or unordered list. Let's explore the following search algorithms, keeping speed in mind. Sequential, linear, search. Binary search. Linear/sequential search on an unordered list. Basic algorithm. Get search criterion, key, get the first record from the file while, record, equals key, and, still more records, get the next record and underscore while. When do we know that there wasn't a record in the list that matched the key? Linear search, sequential search, example implementation. Int linear_search, int list, int n, int key, 4, int I equals 0, ilton, I++, if, list I equals key, return I, return -1, time complexity O, n, unsuccessful search. N times successful search, worst, n times successful search, best, -1 times successful search, average, n/2 times. Linear search questions. What possible modification we can make if the list is a sorted one so as to make sequential search better? Int: when do we know that there wasn't an item in the list that matched the key? Assume you have observed that some of the data items are searched more frequently than others in the list. What modification can be made to make this algorithm better? Homework. Write an implementation for your answers for Q1 and Q2. Sequential search of ordered versus unordered list. If the order was ascending alphabetical on customers' names, how would the search for a Bebo on the ordered list compare with the search on the unordered list? Unordered list. If a Bebo was in the list. If a Bebo was not in the list. Ordered list. If a Bebo was in the list. If a Bebo was not in the list. Ordered versus unordered. Conti. Observation. The search is faster on an ordered list only when the item being searched for is not in the list. Also, keep in mind that the list has to first be placed in order for the ordered search. Conclusion. The efficiency of these algorithms is roughly the same, so, if we need a faster search, we need a completely different algorithm. Binary search. Sequential search is not efficient for large lists because, on average, the sequential search searches half the list. If we have an ordered list and we know how many things are in the list, we can use a different strategy. The binary search gets its name because the algorithm continually divides the list into two parts. Uses the divide and conquer technique to search the list. How a binary search works. Always look at the center value. Each time you get to discard half of the remaining list. Is this fast? Example implementation. Int binary_search, int list, int n, int key, int left equals 0, int right equals n1, int mid, while, left equals right, mid equals left plus right, /2, if, key equals list mid, return mid, else if, key gt list mid, left equals mid plus 1, else right equals mid 1, return -1. How fast is a binary search? Worst case, 11 items in the list took 4 tries. How about the worst case for a list with 32 items? 1 st try list has 16 items, 2 nd try list has 8 items, 3 rd try list has 4 items, 4 th try list has 2 items, 5 th try list has 1 item. How fast is a binary search? Conti. List has 250 items, 1 st try -125 items, 2 nd try -63 items, 3 rd try -32 items, 4 th try -16 items, 5 th try -8 items, 6 th try -4 items, 7 th try -2 items, 8 th try -1 item. List has 512 items, 1 st try -256 items, 2 nd try -128 items, 3 rd try try minus 64 items 4 th try minus 32 items 5 th try minus 16 items 6 th try minus 8 items 7 th try minus 4 items 8 th try minus 2 items 9 th try minus 1 item. Efficiency binary search is one of the fastest algorithms. The computational time for this algorithm is proportional to log2 n. lg(n) means the log to the base 2 of some value of n8 equals 23, lg8 equals 316 equals 24, lg16 equals 4. Therefore, the time complexity is O log. Sorting the binary search is a very fast search algorithm, but the list has to be sorted before we can search it. With binary search to be really efficient, we also need a fast sort algorithm. There are many known sorting algorithms: bubble sort, heap sort, selection sort, merge sort, insertion sort, quick sort. Internal and external sorting. Internal sorting, the process of sorting is done in main memory. The number of elements in main memory is relatively small, less than millions. The input fit into main memory. In this type of sorting, the main advantage is memory is directly addressable, which boosts up performance of the sorting process. External sorting cannot be performed in main memory due to their large input size, i.e., the input is much larger to fit into main memory. Sorting is done on disk or tape. It is device dependent than internal sorting. Common sort algorithms. Bubble sort is the slowest, running in n2 time. Quick sort is the fastest, running in n-lg(n) time. As with searching, the faster the sorting algorithm, the more complex it tends to be. We will examine three sorting algorithms: bubble sort, insertion sort, selection sort. Bubble sort. Suppose we have an array of data which is unsorted. Starting at the front, traverse the array, find the largest item, and move, or bubble, it to the top. With each subsequent iteration, find the next largest item and bubble it up towards the top of the array. Bubble sort is a simple algorithm with a memorable name, and a simple idea. It is an O(n)(2) algorithm and usually called the generic bad algorithm. Obama on bubble sort. When asked the most efficient way to sort 1,032-bit integers, Senator Obama had an answer: www.youtube.com/watch?b=k4rri_ntqca. Implementation. Starting with the first item, assume that it is the largest. Compare it with the second item. If the first is larger, swap the two. Otherwise, assume that the second item is the largest. After one pass, the largest item must be the last in the list. Start at the front again. The second pass will bring the second largest element into the second last position. Repeat n1 times, after which, all entries will be in place. Bubble sort code. Void bubble sort, int a, int size, int I, j, temp, 4, I equals 0, ILT size, I++, /* controls passes through the list. /4, j equals 0, JLT size -1, j++, / performs adjacent comparison. /if, ajgta j+1, / determines if a swap should occur. /temp equals aj, /swap is performed. */ aj equals aj+1, aj+1 equals temp. Example. Consider the unsorted array. To the right, we start with the element in the first location, and move forward. If the current and next items are in order, continue with the next item, otherwise swap the two entries. Example. After one loop, the largest element is in the last location. Repeat the procedure. Example. Now the two largest elements are at the end. Repeat again. Example. With this loop, 5 and 7 are swapped. Example. Finally, we swap the last two entries to order them. At this point, we have a sorted array. Insertion sort. Consider the following observations. A list with one element is sorted in general. If we have a sorted list of items, we can insert a new item to create a sorted list of size k+1. Insertion sort works the same way as arranging your hand when playing cards. Out of the pile of unsorted cards that were dealt to you, you pick up a card and place it in your hand in the correct position relative to the cards you're already holding. Arranging your hand 7 5 7. Arranging your hand 5 6 7 5 7 5 6 7 k 5 6 7 8 k. Insertion sort. Unsorted shaded. Look at second item -5. Compare 5 to 7.5 is smaller, so move 5 to temp. leaving an empty slot in position 2. Move 7 into the empty slot, leaving position 1 open. Move 5 into the open position. 0.775757 K57 VGT LT 123. Insertion sort, cont. Look at next item -6. Compare to first -5. 6 is larger, so leave 5. Compare to next -7. 6 is smaller, so move 6 to temp, leaving an empty slot. Move 7 into the empty slot, leaving position 2 open. Move 6 to the open second position. 77575 K57 VGT LT 123676565. Insertion sort, cont. Look at next item king. Compare to first -5. King is larger, so leave 5 where it is. Compare to next -6. King is larger, so leave 6 where it is. Compare to next -7. King is larger, so leave 7 where it is. 0.7 K56. Insertion sort, cont. 77575 K57 VGT LT 1236785656668 K8 K8K. Implementation. Insertion sort basic idea is unknown. Anot October 12, 2025, 12:29 and 37 seconds plus 03:00 demos /21 demo. Insertion sort.mov. Find the location for an element and move all others up, and insert the element. Steps. 1. The leftmost value can be said to be sorted relative to itself. Thus, we don't need to do anything. 2. Check to see if the second value is smaller than the first one. If it is, swap these two values. The first two values are now relatively sorted. 3. Next, we need to insert the third value into the relatively sorted portion so that after insertion, the portion will still be relatively sorted. 4. Now the first 3 are relatively sorted. 5. Do the same for the remaining items in the list. Implementation. Insertion sort void insertion _sort, int list, int temp, 4, int I equals 1, ILTN, I++, temp equals list I, 4, int j equals I, jgt0 and temp lt list j-1, j, // work backwards through the array finding where temp should go. List j equals list j-1, list j-1 equals temp, / end of inner loop / end of outer loop / end of insertion _sort. Analysis. Insertion sort. How many comparisons? 1 plus 2 plus 3 plus and 1 equals 0 and 2. How many swaps? 1 plus 2 plus 3 plus and 1 equals 0 and 2. How much space? In place algorithm. Selection sort basic idea. Loop through the array from I equals 0 to n-1. Select the smallest element in the array from I to n. Swap this value with value at position I. Unknown. Anot October 12, 2025, 12:31 and 27 seconds plus 03:00 demos /21 demo. Selection sort.mov. Implementation. Selection sort void selection _sort, int list, int I, j, smallest, 4, I equals 0, ILTN, I++, smallest equals I, 4, j equals I plus 1, JLTN, j++, if, list JLT list smallest equals j, / end of inner loop temp equals list smallest equals list I equals temp, / end of outer loop / end of selection _sort. Analysis. Selection sort. How many comparisons? n1 plus n2 plus 1 equals 0 and 2. How many swaps? N equals 0 n. How much space? In place algorithm. End of chapter 2. Next lecture,